Hi students, Professor Nugent here. In this video, we are going to look at the more general case of omitted variable bias. Let's set this up and define some coefficients. Let's define beta j hat for j equals 1 through k as the OLS estimators from the regression of y on x1 through xk, right? We're including xk minus 1 and xk. Then define beta j tilde for j equals 1 through k minus 1 as the OLS estimators from the regression of y on x1 through xk minus 1. So here we have left xk out. Next, define delta tilde for j equals 1 through k minus 1 as the coefficients from a regression of xk on x1 through xk minus 1. Then we can write beta j tilde from this regression is equal to beta j hat plus beta k hat times beta j tilde. The expected value of beta j tilde is equal to the expected value of beta j hat given x plus the expected value of beta k hat given x times delta j tilde, where delta j tilde is just a function of the x's, and so we take that parameter as fixed in repeated samples. And this expected value is equal to beta j plus beta k times delta j tilde. So beta j tilde is going to be biased unless beta k hat equals 0 or delta j tilde equals 0. Now what we want to do now is to prove this result. So let's do that. And we're going to prove this result for x equals 1 without loss of generality. Recall that we can write beta 1 tilde as equal to the sum from I equals 1 to n of R1I tilde times yi all over the sum from I equals 1 to n of R1I tilde squared, where this R1I are the OLS residuals from a regression of x1 on x2 through xk minus 1. Our beta 1 tilde, this is the slope coefficient of y on R1 on this OLS residual, and observe that we are still leaving out xk. Okay, so we're looking at the beta 1 tilde. This is in the case of leaving out xk, and our R1s are the OLS residuals from a regression of x1 on x2 through xk minus 1. Now we can rewrite this numerator as the following. We have the sum from I equals 1 to n of R1I tilde yi, and what I want to do is plug in the regression equation for yi, so that's equal to the sum from I equals 1 to n R1I tilde, and in parentheses we plug in the equation yi, where we have xk in that equation. That's beta 0 hat plus beta 1 hat x1 I all the way through beta k hat xk I plus ui hat. Now why do we include xk in this equation? Because we have yi here, not yi hat, if this were yi hat, then we would leave out the ui hat, but we have yi, so we need to include the ui hat. And it's not yi tilde. Yi tilde is in the regression leaving out xk. So we have yi, and because this is the observation, we need to include the predicted residual. So a couple of things are going to help us simplify this analysis. The OLS residuals have a 0 sample average, and the OLS residuals, these things are uncorrelated with x2 through xk minus 1, right? Because these were derived from a regression of x1 on x2 through xk minus 1. So the R1s represent the part of x1 that are unrelated to x2 through xk minus 1, so they're uncorrelated with x2 through xk minus 1. So multiplying R1I through this equation, the terms in the middle here, x2 through xk minus 1, are going to fall out. One more thing to note, the ui hat also has a 0 sample average, and ui hat are also uncorrelated with x1 through xk. It follows that ui hat is uncorrelated with R1, and so multiplying through, that term is also going to fall out as summing to 0. So this numerator becomes beta 1 hat times the sum from I equals 1 to n of R1I tilde x1I plus beta k hat times the sum from I equals 1 to n of R1I tilde times xki. So this is our numerator. And observe that the sum from I equals 1 to n of R1I tilde x1I, this is equal to the sum from I equals 1 to n of R1I tilde squared. Contains the same information. And this is the denominator, the sum from I equals 1 to n of R1I squared, the denominator of the expression for beta 1 tilde. So we can plug this back into the expression at the top of the board. So let's do just that. I'm going to rewrite this thing at the top of the board. So we have beta 1 tilde is equal to beta 1 hat times the sum from I equals 1 to n of R1 I tilde x1 I plus beta k hat sum from I equals 1 to n R1 I tilde xki all over sum from I equals 1 to n of R1 I tilde squared. And because the sum from I equals 1 to n of R1 I tilde x1 I equals the sum from I equals 1 to n of R1 I tilde squared, this becomes beta 1 hat plus beta k hat times the sum from I equals 1 to n of R1 1I x ki all over the sum from I equals 1 to n of r1I squared. Tildes here, tildes there, and this equals our delta 1. Beta 1 hat plus beta k hat delta 1, which is what we wanted to show.